Hello, and welcome to our webinar today on microelectronic component reliability. We thank you for your interest in this topic and in EAG, and we hope you find it valuable. Um, we originally recorded this live or had a live session where there was some Q&A. This is not a live session, of course, so if you have questions, please feel free to reach out to us anytime. We'd love to hear from you. But without further delay, let's get started. My name is RM Sarkissian. I'm the General Manager of the Engineering Sciences Division at EAG. I have spent my career in the lab services space and very excited to be part of EAG and leading this team. Joining me today are Chris Brigham. Chris has decades of experience in reliability, quality, and operational roles and continues to actively participate in industry standard setting organizations. Also joining us is Tom Napier. Tom's another seasoned industry vet. Tom heads our reliability service business and has a very strong test solutions background, which is valuable as we develop component plans to both stress and test various components. A little bit about the Engineering Sciences Division at EAG. What we've assembled is a range of services in the area of test, reliability, failure analysis, and debug that are generally all activities required in new product introduction phases and in ongoing product improvement efforts. Today, of course, we're going to focus on the reliability portion of what we do, but it's important to understand that having all of these services tied together in one cohesive, multidisciplinary approach helps us solve problems much more rapidly. As an example of that, if you are able to quickly test the components that you are putting under reliability stress, that's going to give you a very, very quick feedback loop for making changes or debugging the devices. Also being able to quickly investigate maybe early mortality as the result of failure from some reliability stresses and strains is also going to be something that's going to save valuable time in getting a product to market. So in terms of the content today, we're first going to start with a little bit of a reliability 101. We'll go through some of the basics of reliability. We'll then get into component level reliability. Firstly, qualification, which is the when, what, and why of reliability. And tied to that are some examples of when failures occur. We'll then talk about how to manage change. And then finally, we'll look at what does all of this data tell us of what is happening in component reliability is being driven by the changes in how we use them or the technology trends that are occurring in the marketplace. So one big area is increased complexity. So this comes in more components being in more products. Another aspect of that is process technology itself advancing. So think about Moore's law and miniaturization there. And then a third would be packaging and the packaging technology advancing with new material sets and form factors. So all of that makes for just increasing complexity overall. Second is increasing the applications that we are rolling out. So consider all of these new markets, automotive, mobile infrastructure, all of these various things that you hear about. Well, each of those applications are areas where there's additional microelectronic content coming into being, and we've got to deal with the reliability aspect of that. And then a third major area is the increased reliance. So as more and more of our infrastructure and critical systems packed with microelectronic components, reliability is going to become a greater concern. Something that we're just going to need to prepare for and pay attention to. So let's give a couple of definitions for framing what quality and reliability are all about. Quality is the conformance to the requirements. And reliability, on the other hand, is the quality measured over time. So the product reliability then is the product's ability to function with a given performance limit under a specified operating condition over its intended operating life. So use case is everything, and it's what you want to focus on and consider when you think about the quality and reliability. This is a graphical representation of product lifetime that you may have seen before, and it's referred to as the bathtub curve. And it's a very standard representation of failures over time for products. And you'll see that in the early time period, you get typically early fallout, early mortality events. And that's followed by sustained period of useful life when those early failures have been shaken out. And then you get, of course, increased failures toward the end where you're really wearing out or getting to the end of life of products. So the test and qualification plans that we execute are designed to help accelerate this timeline so that we can understand these limits and either work within them or perhaps redesign a product to better conform to the use case we're going to have. So when do you do qualification? Well, generally you do it when you introduce new products or you make a significant enough change to the product. So new and or change events are things like new IC designs, a new package, a change in the market you're serving. So in other words, you're going to a more stringent market perhaps. An IC design change would be major enough. A change in the fabrication process itself is another event. And then finally on this list is a change in the packaging. So this can be where folks get into trouble in terms of managing these changes, in that some may say the change was not significant enough to warrant requalification, but too many of those changes added up may have your product drift to a place where the current product is materially different from what you started with. In all cases, be careful managing your way through this change, and when you need to requalify, you do it so you don't wind up getting into trouble. Standards are an area where there are some helpful baselines, and standards give us some helpful baselines that we can follow. A couple useful things about standards: they do create uniform methodology for us, and they also create a common language for describing methodology. There are some industry standards groups that exist, and many of the test methodologies we perform are laid out in the specs by such groups. And while standards have been used a long time successfully, it's important to emphasize that adherence to the standards without some understanding of how they relate to your product or the market you plan to serve is not enough. So, get help from experts when you're not sure. So thinking about some common standards, there's some listed here, and they've got some specific reference documents called out. I'm not going to go into each of these, but just know that each of these specifications will have fairly explicit, detailed processes outlined for how to conduct these tests. But why they can be prescriptive, they often leave some room for interpretation. So be careful when they do. These specs also get updated from time to time as industry learnings are shared and adopted. So it's important to make sure you know what revision of the spec you're using and why. So he's not well known for his work in reliability, but Ben Franklin was certainly a wise man. And he left us with this quote: "By failing to prepare, you are preparing to fail." These are very wise words. The best thing you can do is plan well, give yourself the time and resources to test things properly so you don't set yourself up and your product up for unexpected failures. And with that, I will turn it over to Tom.
The device qualification is separated into two parts: the die and the package. The die and the package have their own set of reliability stresses. The die uses stresses such as the high temperature operating life and ESD, which are related to the die design and fabrication. The package stresses focus on things that will make the package degrade over its lifetime, such as its temperature and humidity. The objective of the qualification is to validate the device will work over its lifetime. And to do this, you need to accelerate the lifetime to a short span of time. And this acceleration occurs through the stress conditions. And one way is you provide higher temperature than the device would normally operate at. You provide a higher voltage than it would normally operate at, you use humidity, and you apply mechanical stresses. Now I'm going to start off with the IC, the die qualification flow. And here I have a flow diagram. And in the IC die qualification, we will run the ESD using the charged device model, the human body model, latch up, the high temperature operating life, and high temperature storage life to validate that the die, the IC chip itself, will work over its lifetime. High temperature operating life. High temperature operating life is performed to validate that your IC, the die, will continue to operate to its specifications over its lifetime. HTOL is one of the more complex stresses because the device is operated in a dynamic mode with the transistors toggling. This means you must typically apply some type of stimulus to the device, such as a clock minimum, or you need to provide a complete vector set to make sure that most of the gates inside the IC are toggling. It is also common for the device outputs to be monitored to verify the device is operating properly throughout the HTOL stress, and you're able to tell at some point if the device fails. Acceleration of the lifetime is achieved by operating the device at a higher temperature than the nominal use temperature and at a higher operating voltage than the nominal use voltage. The Arrhenius equation can be used to calculate the lifetime acceleration factor based on the increased operating voltage and higher temperature. A typical acceleration factor of 80 for a 1,000 hour H2L run would equate to 80,000 hours of lifetime. 80,000 hours is more than 9 years. During H2L, the device must be operated with a minimum junction temperature of 125 C. You may choose to use a higher temperature to increase the temperature acceleration factor. A device is typically biased 5 to 10% higher than the nominal operating voltage to achieve the voltage acceleration factor. Following the H2L, the device must be electrically tested. Typically, this is done on ATE to verify the device is fully functional and meets all its specifications. The electrical testing also measures critical parameters. So the critical parameters will be compared with the pre-H2O measurements with the post-H2O measurements to see if there's any drift in these critical parameters, because these parameters may indicate the device may fail in the future. You may refer to the JEDEC spec for additional details on high temperature operating life. The next stress I'm going to talk about is the high temperature storage life. And this stress, again, is based on stress in the die or chip. And it's looked to verify that the device will not be damaged by storage at elevated temperatures. Now, often after the device is manufactured and shipped, it may be stored in a non-optimal condition for days, weeks, months, even years before it is used and assembled onto the PCBA. And this stress is to validate that this storage at a higher temperature will not damage the device and it will still be functional when it's used. Now, the failure mechanisms that occur during HTSL are diffusion, oxidation, intermetallic growth, or chemical degradation of the package. HTSL is one of the more simpler type of stresses to execute because it's a non-bias stress. It's executed at one temperature. The typical temperature for HTOL is 150 C for 1,000 hours. Now, following the HTSL stress, the device must be electrically tested to verify that it's still functional and meets all its electrical parameters. Also, there must be an optical inspection of the package performed to verify that the HTSL test caused no physical damage such as cracking or chipping. Refer to the JEDEC spec for more details on the high temperature storage life. This slide shows some examples of failure mechanisms that occur because of high temperature storage life. The intermetallic growth will cause separation between metallic layers, and this is common with the ball bond, where we see a lift on the image on the left, and there we see a copper wire post lift in the image on the middle, and on the right is a good ball bond. There are two electrostatic discharge tests that are performed. The first I'm going to look at is the human body model, HBM. Now this test is performed to validate that your device will not be damaged during the assembly process or manufacturing process when handled by humans. and an electrostatic discharge goes from the unit into the device. There are different classes of HBM voltages that you may classify your device to. These range in levels from on the very low end to the minus 50 volts to on the very high end at 8,000 volts. The most common are in the 1,000 and 2,000 volt range. Now, during the stress, positive and negative voltage pulses are applied to each pin, and they're applied to each pin in relationship to each power and ground domain. Now, the HBM stress itself does not do any validation that whether the device is damaged or not, so it must be tested following this to verify that it's still fully functional and passes all its specifications. Refer to the JetXpect JS001 for more details on human body model testing. The next qualification test we'll look at is another ESD test. This is the charged device model, otherwise known as CDM. And like HBM, CDM is used to validate that your device will not be damaged during the assembly process. This is to validate that as your device is moved on assembly equipment, it will build up a charge on it. And when the device becomes in close contact on a ground path, it will discharge into that path. And we want to make sure the device will function after this and not be damaged because of this discharge. This discharge occurs in a few nanoseconds and can be greater than 10 amps. Now, during the CDM test, there are different voltage classifications that you can classify your device to for less than 125 volts up to greater than 1,000 volts. The most common are the 200 to 500 volt range. Now, each pin on the device will be tested for a negative and a positive charge voltage. A curve trace may be performed before and after the CDM test to validate that there's no changes in the IL characteristics. The device also must be electrically tested to validate that it still meets all its specifications and is fully functional. Refer to the JetXpect JS-002 for more details on the ESD charge device model testing. The next stress we look at is the latch-up. Latch-up can occur in CMOS, NMOS, bi-CMOS circuits where parasitic circuits of PNP and NPN transistors form a thyristor circuit. This thyristor circuit creates a low impedance path between the power planes or power plane to ground. In the latch-up state, the device will draw high current, which will potentially damage the device. Now, to test latch-up, we will power the device up with nominal power and IO voltages, and the device should be in a stable low-power mode. The latch-up test is broken into two parts. One part deals with the IO pins, the other part with the power supplies. In the IO pin testing, each IO pin is pulsed with a negative and positive current when the pin is driven high and low. The current of all the power supplies are measured before and after each pin is pulsed to verify if the device entered a latch-up state. The power supply section is similar. Here, each power supply pin is pulsed with a voltage that's 1.5 times the nominal VDD. Again, the currents of the power supplies are measured before and after this. The power supplies are pulsed to verify if the device entered a latch-up state. Now, the latch-up state passed-out criteria is that the power supply post-current must be less than 1.4 times the pre-test current. There is another condition that if the power supply current is very low, less than 25 milliamps, the passed-out criteria is different. Then the post-current must be less than 10 milliamps higher than the pre-test current. Now, there are two classes of latch-up test. One class is performed at room temperature. The second class is performed at an elevated temperature of either the case temperature or the maximum junction temperature. Electrical testing must be performed after the latch-up test to verify that the devices are fully functional and meet all the specifications. Refer to the JetXpect for more details on the latch-up test. Now here I'll summarize the IC part of the qualification. This does not include the package qual, just the IC, the die itself qualification. This table shows the stress that's being run, the JetX standard, the conditions the typical conditions that you run this stress under, the required number of lots and units, and the number of fails allowed for each test. Now, in addition to the high temperature operating life, there's the early life failure rate, ELFR test. This test is very similar to H2L, typically run at the same temperature, but instead of looking for end-of-life fails, it looks for infant mortality fails. A few slides earlier, we saw the bathtub curve, where the left side of the bathtub curve shows the early life failures, the right side shows the end of life failures. So here for ELFR, we're focused on the left side, and we want to understand the magnitude of that slope there, of how many fails are there. And that's what ELFR is performed to figure that out. The typical duration of ELFR is 48 hours, and it may be performed on thousands of units. ELFR provides a measurement, fails per million, or FPM, for the number of early life fails that you would expect. The JEDEC standard JESD 47 has a table in it that provides the number of units required for ELFR dependent on your desired number of fails per million. Now, also in this table here, I have the electrical parameter assessment. This is also a part of HTOL. It is a test that's performed at ATE before and after HTOL, where critical parameters are measured on the device before the HTOL and after the HTOL, and then to compare to see what the delta is in those parameters. If the delta is there's too much drift between the pre-HTOL and the post-HTOL, this may be an indicator that the device will fail in its lifetime or drift out of specification. Okay. I will now move on to talking about the package qual. Previously, we were talking about the IC qualification, which dealt with the die or the chip itself. The package qual will talk about how we qualify the package. Package qual starts with preconditioning. In this flow diagram here, we can see preconditioning occurs first. After preconditioning, the units that go through precondition will be split into going through the other stresses, such as the bias task, temperature humidity bias, temperature cycling, or unbiased task. Preconditioning. Preconditioning is performed to verify that the device will not be affected by the assembly process or the solder reflow of the device onto the PCBA. The first step of the preconditioning is to temperature cycle the device between -40 C to +60 C, 5 cycles. This is to simulate the device in transit that it may go through different temperature zones as it is transferred from your manufacturing floor to the final PCBA floor, where it will be assembled onto the PCBA. Following the temperature cycle, the device will go into bake. The bake is to remove any moisture from the device to set a baseline that there's no moisture in the device before the moisture soak step. The moisture soak step is to simulate the device sitting on the factory floor after it's been removed from its vacuum bag, but before it's been soldered onto the PCBA. And this may be in a semi-humid environment where the device is soaking up moisture from the environment around it before it is actually assembled on the PCBA. And there are different levels of moisture soak levels, and these simulate the different durations of time it may be sitting on the factory floor that you're going to qualify it to. One of the more common is the moisture soak level 3. This will equate to 168 hours of floor life after it's been removed from the vacuum bag before it is assembled onto the PCBA. After the moisture soak level, now the device goes into solder reflow to simulate the device being attached to the PCBA. The solder reflow will be repeated 3 times, and this is to simulate the device as it may go through the reflow process on top of the board, bottom of the board, repair. So it gets repeated. The same solder reflow gets repeated 3 times. The diagram on the right side of the slide shows a solder reflow temperature profile over time. Now, each device has its own specification about how it's to be attached to a PCBA. So there's a specific solder reflow. Now, during preconditioning, this solder reflow is duplicated to match the device specification. Following the preconditioning, the device must be electrically tested to verify that it still meets all its specifications, it's still fully functional. And you may refer to the JEDEC spec for more details on preconditioning and moisture soak. Popcorn effect. This slide shows the most common failure mechanism for preconditioning. Here we see in step 1 that during the moisture soak level of preconditioning, the device is absorbing moisture within it. In step 2, this moisture becomes trapped, not released. And then as we go into the solder reflow, the device is heated up to range of 260 degrees C for the reflow. This moisture then expands and will cause delamination within the package, which is a failure mechanism. If it's severe enough, it will even cause physical, observable damage to the package, such as swelling or cracking, as we see in steps 4 and 5. It is recommended to perform an analysis of a sample of the units that go through preconditioning before and after preconditioning using that confocal scanning microscope, also known as CSAM. The CSAM is looking for delamination in the package following the preconditioning. This is an example of a package that has delamination shown here in the lower right-hand corner within that red circle. Here we're looking at the package qualification flow again. Now we're looking at the stresses following preconditioning. The units that went through preconditioning will now be split into different groups. Part of those units will go through bias test or THB. Some of the units will go through temperature cycling, and some of the units will go through unbiased test in a typical package qualification flow. Highly accelerated stress test, or known as HAST. This test is performed to test a package for corrosion resistance, and the package insulation does not allow moisture inside the package. The failure mechanisms seen from high bias test are corrosion, oxidation, electromigration, delamination. Previously, the temperature humidity bias test 8585 was used to test for this. Due to the 1,000-hour duration of THB, it has largely been replaced with the bias test. There are two different temperature ranges and durations per bias test. The 130C, 85% relative humidity for 96 hours is recommended for leaded packages. The 110C, 85% humidity for 264 hours is recommended for ball griddle rate packages. The bias test, as the name says, is a bias test. The device should be in a low power state. The voltage levels on the I/O pin should be alternated between high and low levels as much as possible. Now, this test is designed for devices that are in a low power state that do not draw a lot of current. If the junction temperature of the device is 10 degrees greater than the 130C or the 110C, then the device power needs to be cycled on and off. This is to allow the device to cool enough to allow moisture to enter the package. Following the bias test, the devices must be electrically tested on ATE to verify the device is fully functional and meets the specifications. You may refer to the JEDEC spec for JESD 22-A110 for more details on bias test. Here we're looking at a failure mechanism following bias test. During the electrical testing, one of the things that if a failure occurs, probably one of the more typical failures that occur during following HAST is higher leakage. The bias test environment of the electrical biasing, the temperature and humidity create an electrical chemical reaction that promotes the dendrite growth. This dendrite growth occurs in materials such as the silver, copper, or tin within the package. This dendrite growth will create a leakage between different circuits of the package and cause it to fail the electrical testing. Temperature humidity bias, also known as 8585. This test is another bias test. It is extremely similar to the bias test, and it tries to promote the same type of failure mechanisms. The major difference is that the temperature humidity bias test is much longer. It's done for 1,000 hours and it's performed at 85C and 85% relative humidity. It has largely been replaced by bias test because of the much longer duration of this test. Most people prefer the bias test. For some devices that are high power, the bias test may not be suitable and they may be more suitable for the THB. You may refer to the JEDEC spec 22-A101 for more details on temperature humidity bias testing. Unbiased, highly accelerated stress test. This test is done to focus only on the corrosion resistance and package insulation failures modes from temperature and humidity, and not those related to voltage biasing. This test is extremely similar to the bias test, except for the bias test, except for there's no bias here. so there's no concern for power dissipation. So the failure mechanisms seen from unbiased tests are corrosion, oxidation, delamination, and not from electrical migration. Following the biased test, you must electrically test it, typically on ATE, to verify that they're fully functional and your device meets all its specifications. Please refer to the JEDEC spec for more information on the unbiased test. Temperature cycling. The temperature cycling verifies the components and solder interconnects are capable of not being damaged with alternating high and low temperatures. The temperature cycling may induce mechanical failures such as cracking, delamination, and warping in the package. Temperature cycling is a non-biased test. There are different classifications for the temperature range and the number of cycles to be performed. Condition B of minus 55 C to plus 125 C for 700 cycles is the most common. Following the temperature cycling, the device must be electrically tested to verify that it's fully functional and meets all its specifications. You may refer to the JEDEC spec for more details on temperature cycling. On this slide, we're looking at different examples of failures that occurred because of temperature cycling. These failures all show up as cracks in the die, the substrate, solder bumps, bond wires, or the via structures. In the package, different materials will have different thermal expansion coefficients, and as the temperature cycle, the expansion and contraction of these materials will be different from material to material and create a mechanical stress and potentially crack. Here we have a summary of the package qualification stresses. So we have the stress name, the JEDEC specification number, the conditions per the JEDEC, and the number of fails allowed per the JEDEC specification, plus the number of lots and units to run per the JEDEC spec. As we discussed in the presentation, the precondition is performed first, and then the units proceed to the biased test, or THB, to the temperature cycling and unbiased test. You would not run both THB and biased test, one or the other. Earlier, we heard from Ben Franklin about preparing and how important it is to prepare. Now, Winston Churchill tells us we need to actually not only prepare, but also look at the results. However beautiful the strategy, you should occasionally look at the results. Thank you for attending my part of the talk today. I will now hand it over to Chris to talk about managing change and key reliability metrics.
Greetings, this is Chris Brigham, and so you've now heard from Aram and you've heard from Tom talking about standards, talking about qualification stress tests. So now you think you're out of the woods, right? Wrong. Change is going to happen. It's basically inevitable, and it's going to happen under the premise of the fact that it's going to be a change for the better. Usually, a subtle change is not necessarily a big issue, but sometimes a subtle change can be a showstopper. By change, I'm talking about a change in a process, a change to packaging, a change in assembly, a change to a test. They all have to be carefully looked at to make certain of their impact on the product reliability from what you've already done to qualify a product. So the following two slides are going to talk about some of the recommendations of things to look at for several types of major change. Okay, so first let's talk about process changes. If you look horizontally, you'll see the various types of REL stresses that are run, anything from H2L all the way to TDB. If you look vertically, you'll see some examples of what the industry considers to be major changes. An active circuit element change, a metallization change, a gate oxide change, a contact change, something as significant as a wafer diameter change, a fab site relocation or change, or die thickness. What you'll see are the letters R and the letters C under the block by the stress. So you pick the recommended stress, and then you also look at what they also want you to consider. It takes a bit of finesse to understand exactly the significance of the change you're talking about, so a little bit of experience would help here, or feel free to give us a yell and we can give you some advice as to what we think you should consider. Okay, so we've talked about process. Now let's talk about package and assembly change. It's the same basic premise. You have a vertical column of specific types of change and a horizontal columns of stresses that they recommend you use. Again, R are recommended stresses for that particular change, and a C is a stress you might want to consider depending on your exact application. These tables, or these previous slide and this slide, come from a JEDEC standard that's pretty well widely accepted as something you need to consider when you're trying to make a change. Okay, so thanks for hanging in there so far. Now I'm going to try to confuse you a little bit with some of the more common reliability terms that you might hear. Some of you may have already used them, but let me basically try to go through and explain kind of what they mean, because likely you'll hear about them when you're talking about the reliability of a product or package or process. All right, let's talk about the four terms: MTBF, the most common, MTTR, MTTF, and FIT. They're basically terms based on methods and procedures for life cycle prediction. These terms define what the life cycle is going to be for a specific product. MTBF is the mean time between failure. MTTR is the mean time to repair. MTTF is the mean time to failure. And then FIT is basically a failure in time. You're probably most likely going to hear about MTBF or FIT rates. But basically, they're ways of providing a numeric value that's based on a bunch of data that you can compile and calculate what the failure rate is going to be resulting from an expected performance. Okay, so let's go back to our bathtub curve, or basically a graph of what the product lifetime should consist of. To the left of the dotted line, you'll see infant mortality. This is what you initially would expect to have as a failure. The center or bottom of the curve is basically your useful life, and to the right, it's basically the end of life or the wear-out period. What you ideally want to do is get past that first set of dotted lines to get to the useful life of a product. Okay, let's talk MTBF, the mean time between failures. It's basically a reliability term where you try to calculate the failures per million hours of a given product or process that you're trying to validate. It's the most common inquiry in a product's life. It's an important factor in making a decision for an end user, and it's more important for industries and integrators than it is for actual consumers. Okay, now let's talk about mean time to repair. It's the time needed to repair a failed module or component, quite simply. Taking too long to repair a product drives up the cost of an installation, and in the long run, due to downtime until a new part arrives, the possible window of time required to schedule the installation is long. To avoid MTTR, many companies purchase spare parts so that the replacement can be installed quickly. Okay, so the third similar sounding term is the mean time to failure, or MTTF. Basically, it's a measure of reliability for repairable systems. It's the mean time that it's expected until the first failure of a piece of equipment, a component, or a module is occurred. It's a statistical value, and it's a mean over a long period of time or a large number of units. Technically, MTBF should be used only in reference to a repairable item, while MTTF should be used for non-repairable items. Okay, so the fourth and final term I want to talk about today is something called failure in time, or FIT, commonly called FIT rate. It's just basically another way of reporting MTBF. It reports the number of expected failures per 1 billion hours of operation for a given unit. It's particularly common in the semiconductor industry, but it's also commonly used by component manufacturers as well. FIT can be quantified in a various number of ways. For example, 1,000 devices for 1 million hours, or 1 million devices for 1,000 hours. FIT and confidence level, or confidence limits, are often provided together. Okay, so MTBF is probably the most common term that you hear. We talked about it a little bit earlier, but it's also commonly a source of misconception. MTBF value is equivalent to the expected number of operating hours before a product fails or the service life. It's actually a very complex calculation. There's an algorithm that factors in all of the product's components to reach a sum of the life cycles. And on the slide, you'll see a formula, which is basically the reciprocal of the sum of all of the failure rates of all of the components or aspects of the module, board, product, system, whatever you're talking about. It's not just a simple formula, and it should be performed by certified or educated personnel. Each component, as well as other factors such as operating temperature range, storage temperature range, also must be considered in calculating MTBF. Okay, so hopefully I haven't confused you too much. Here's some considerations to keep in mind. MTTR, MTTF, and FIT apply to specific products or specific components. However, MTBF still remains to be a basic measure of a system's reliability for most products, and it's widely misunderstood. It's still regarded as a useful tool when considering the purchase and installation of a product, and along with obtaining the MTBF value, you want to ask questions regarding how current the information is, on what standards it was based on, so you ensure on choosing the most appropriate product for your installation. Thanks so much for your time, and now I'm going to turn it over to Aram.
Well, thank you very much, Chris and Tom, both of you, for those terrific presentations. Just want to leave you with some final thoughts. One, of course, is electronic components are proliferating rapidly. They are everywhere and in everything. So it's important to know the use cases and know, therefore, figure out the reliability that you're going to need in those use cases. You're going to have to think about both the device and the packages that those devices are in, and know about the standards and when to apply them. What industry are you really gunning for, and what set of specifications and standards are the governing body there. And finally, a well-executed qualification plan is going to provide you a better understanding of the reliability of your product, which will pay you huge, huge dividends as your product heads out into the world. So as you continue your product development journeys, we wish you all the best. And certainly if you have any questions, feel free to reach out to us anytime. Thanks for your time.